Hello, folks. So, we are going to pick up on chapter 17, where we're going to focus on advanced equilibrium situations such as buffers, titration reactions, solubility products, and formation of aqueous complexes. Well, let's go ahead and get started by talking about buffers. Like most of the chapters are kind of more or less standalone, this one is building directly off of our last chapter. So the idea here is that what if we apply Le Chatelier's principle to acid base? What if instead of just saying the reaction goes and we reach equilibrium, what happens if we do something like add something? What happens if we add additional products? Or what happens if there's already products available? What would that do for our acid-base solutions? Well, Le Chatelier says that when you add a product, reaction will naturally want to shift back towards reactants. So while some dissociation will still occur, there will be less than if we had no conjugate acid or conjugate base. So, hypothetically, let's look at a solution of HF. We have a 1 molar solution of HF. If we look at the initial situation, like what would happen if it's just pure HF? Well, we have 0 protons and 0 fluoride. Technically, it's not 0, but it's essentially 0. And so when we do the ice table, X hydronium forms, X fluoride forms, and 1 minus X HF goes away. And so when we set up our expression, 1 minus X, we can simplify that, and we get that the concentration is 2.6 times 10 to the negative second, which means we're going to have pH of something like 1 something. It's a pH of 1.58. So pretty acidic. Now, hypothetically, if we were to add even just 6.3 grams of sodium fluoride, 6.3 grams, if we divide by the molar mass, it would be about 0.15 molar. So just even 0.15 molar of product. Because the equilibrium expression, we have essentially 0 hydronium, it would still dissociate and would still form more fluoride. But the fact we have 0.15 molar fluoride present means less is going to be formed. So our equation is no longer 1.0 minus X with X and X on top. It's now 0.15 plus X times X. A little bit more complicated to solve. We could still solve quadratically. But what we get is, instead, 4.5 times 10 to the negative third instead. And that would give us a pH of 2.34. Just by adding like a sixth of a molar of conjugate base, essentially, we have suddenly pH is going from 1.5859, let's just say 1.6 to 2.3. It has changed by almost like a factor of 10, the concentration. So what happens if I were to add enough sodium fluoride till we have equal molar concentrations of HF and F minus? Now we still have ridiculously small amounts of hydronium. Whether you say 0 or you say 10 to the negative 7th, it's still so small that it's not at equilibrium yet. So with that in mind, we're still going to get some dissociation. So it's still going to be minus X and plus X on the right. And so we set that up essentially 1 minus x and 1 plus x, those x's are going to be so small that they're negligible. And so it simplifies so that it's 6.8 times 10 to the negative fourth. So when we have equal amounts of acid and conjugate base, the pH has gone to now 3.16. So essentially it's gone from 1.6 to 2.3 to 3.2. It has slowly going up by a factor of 10 each time, just about, as the amount of fluoride goes in. So we're looking at a situation that is far less acidic than the initial situation. Far less acidic because of the conjugate base being there. This is referred to as a buffer. A buffer is a solution that is resistant to change in the pH that is created by mixing a weak acid with its conjugate base, or a weak base with its conjugate acid. The idea is that these two have a balancing effect that keep this from having drastic changes in pH. Buffers are extremely important in various biological systems, where drastic changes in pH can be very destructive. Enzymes fold based on certain pHs. That above or below a certain pH, the enzyme starts to denature and they no longer work. So certain things do not work in too strong of acids or too strong of bases. Blood is buffered. Stomach acid is buffered. Seawater is buffered. Even most of our fresh water is somewhat buffered with alkalinity of carbonate dissolving into water from the CO2, which is going to create some buffering effect that is going to neutralize some small amounts of acid that is naturally in the rain, so that when it doesn't rain, it doesn't kill all the fish. So these situations can accept a small amount of acid without changing the pH in a drastic way. The buffers work by essentially neutralizing any hydronium or pure hydroxide upon their addition. So if you add a strong acid of any type, the HA neutralizes the base to form water and some of the conjugate base, or the A- neutralizes some of the hydronium to form the conjugate, the original acid. So depending on what is added, it has the ability to essentially counteract a small portion of that. Now, because pure hydronium or pure hydroxide are removed, the equation still becomes a HA A- balancing effect that is a Ka expression. However, if there's any pure hydronium present, the pH just goes straight to like strong acid scenarios. So, or something similar. So, as long as there's weak acid and conjugate base remaining, the pH remains buffered. But there is a limit. Once we've added too much strong acid or too much strong base, and we completely remove one of these ions from either side, the acid conjugate bases, we'll see a large jump in pH. So once we fully neutralize all the A- with H3O pluses, it's going to jump to very acidic. Or as soon as we add enough hydroxide to remove all the HAs, it's going to jump to very basic. Because it doesn't take much OH to jump a huge amount. Now, so in these situations, only H plus is generally left unknown to us. And we can solve this by rearranging our equation so that we now have HA times Ka over A minus. So long as we know these concentrations, we can find H plus. Now, We will often rearrange this and write this in an easier way, but you can, by all means, use it in the form and fashion that we have right there. But if you take the co-logarithm to each side, you separate our logs, you get basically what is known as the Henderson-Hasselbalch equation, which looks at pH is equal to the pKa plus the log of A minus over HA. You'll notice it was flipped around up there, but the negative logarithm switches to a positive logarithm, and thus flipping our ratios. But so if you know the pKa, you can easily see how adding base or adding acid to here will affect our pH. Now, with that in mind, since this is a ratio of acid and base and it's a logarithmic ratio, we have a little bit of a problem. So that when these two are equal, regardless of whatever the concentrations are, whenever the concentration of HA and A minus are equal, you get the log of 1. The log of 1 is equal to 0. So in the rare cases when HA and A minus are equal, pH is equal to the pKa. So that's our starting middle point. You can have more A minus or you can have more HA, but the starting middle point where they're both equal, pH is equal to pKa. Now, because this is a logarithmic ratio, for every factor of a 10 that A minus is over HA or HA is over A minus, we only change the pKa, or we only change the pH by a factor of 1 unit because it's a logarithmic scale. So when we make this, we can mix acid solution with the conjugate base salt, for example, or base with the conjugate acid salt, or we could take a high concentration of buffer and partially neutralize it. But generally speaking, these buffers work effectively only within about plus or minus 1 pH unit away from the pKa. Beyond that, the buffers do not work very well because remember, this is a logarithmic scale. So we're saying I'm going to have one guy, if I'm doing a full 1 unit away, I have to have a concentration difference of 10 times. So whether that's 1 molar for one guy and 0.1 molar for the other guy, or 5 molar in one guy and 0.5 molar in the other guy, you're looking at a big difference. So that one's going to easily run out quickly, the other is going to be around for quite a while. So unless you're using incredibly high concentrations, it's going to be very easy to neutralize one of them. It's not going to be a very effective buffer against, say, acids. It will be effective against bases, but not acids. So that doesn't really make a buffer work super well. So when we figure out, when we're making a buffer, you want two things. You want to decide, knowing the desired pH of your buffer, you need to pick a compound that has a pKa somewhat similar to the desired pH. And you need to make sure your buffer itself is not likely to react with any of the compounds you might be treating it with. So with that in mind, you can easily pick a buffer. So with this in mind, this example, which of the following solutions would you use to make a buffer with a pH of 3.5? Then what ratio of acid and base would you need? So with this in mind, we have NH3, NH4 plus, Ka of 5.69, 10 to the negative 10th. We have formic acid, formate, with Ka of 1.8 times 10 to the negative 4th. We have carbonic acid, sodium bicarbonate, 4.46 times 10 to the negative 7th. And we have sulfuric acid, well, hydrogen sulfate, with a pKa of 1.03 times 10 to the negative 2nd. So we're going to use more or less the pKa to help guide this. So with that in mind, let's go to the doc cam. So the pKa, remember, is just the log of the Ka. So if I take the log of 5.69 times 10 root negative 10, I get, so pKa of 9.2. That's nowhere close. Okay. That's nowhere close to our desired pH of 3.5. So negative log of 1.8 times 10 power 10 power negative 4. I can tell you right there, this one's going to be good. 3.74. Okay, that's going to be close. That's within 1 pH unit. But let's just show the other ones just to make sure. Negative log 4.46 times 10 power negative 7. 6.35. That's definitely too far away. And negative log of 103 is 10 to negative 2nd. Oh, for God's sake. Negative 2nd. And that's 1.98. Close, but not quite close enough. I'd rather have the 3.74 to get it to 3.5. So with that in mind, 3.5 equals 3.74 plus log of A minus over HA. So the difference right here is negative 0.24 log. To get rid of the log, we do the inverse log. And this will be the ratio. Inverse log of negative 0.24 is 0.575 A minus over HA. So we want slightly more HA. Whatever HA is, we want whatever the concentration of HA is, we want 57.5% of A minus. So if this is 1 molar, you'd have a 1 to 0.575 ratio of AHA and A minus. But more HA makes it more acidic, so the pH drops down. More A minus would make it more basic, and so pH would jump up. So take that with it with a grain of salt. That's doing that. Now if I did the inverse relationship, just the inverse of that, that's how you get the 1.74. That 1 over 0.575 is 1.74. So whatever you use for A minus would use almost twice as much for HA. Now this last one is a practice one. What is the pH of acetic acid and sodium acetate? These situations. So 0.32 HA and 0.5 A minus when the Ka is 1.8 times 10 to the negative 5th. And what about when I have 0.45 HA and 0.24 A minus, and the KB is 1.8 times 10 to the negative 5th. Now, as I said, I will solve this two different ways. I'll solve the first one without the Henderson-Hasselbalch. Henderson-Hasselbalch isn't needed. You can just say H plus is equal to Ka HA over A minus. So H plus is 1.8 times 10 to the negative fifth times 0.32, 0.5. So the concentration of H plus is going to be slightly less than 1.8. 8 times 10 power negative 5 times 0.32 divided by 0.5. So you'd get, that's 1.15. So that equals 1.15 times 10 to the negative fifth. You take the negative log of that, the negative log of that, and the negative log gives you 4.93. Slightly acidic, but slightly less acidic. 4.94 pH. Okay, the second problem is a base. You notice it has a Kb. Well, POH is going to be equal to the pKb plus log of, in this case, base over conjugate acid. Essentially A minus over AHA. Well, the pKb is going to be negative log of 1.8 times 10 to the negative fifth. That's going to be 4.74. 4.74. And I know that because it's an easy one to remember, because notice the Ka and the Kb are twins. Plus log of, well, how much we have slightly more acid than we have base. So we're going to add the 4.74 plus the log of 0.45 over 0.24 and we get 501. That's our POH. So that's our POH. We'll say 502. Well, pH is equal to 14 minus POH. So 14 in the flip the sign, so we get 8.98. 8.98 is our pH. I know I've kind of crowded my answer down there. Forgive me, or don't. But that is 4.94 and 502, which goes to 8.98. So that is essentially how we work through a buffer. In most situations where Ka is small and the concentrations are large, you can ignore any X's. You don't really need an ice table if you just use the Henderson-Hasselbalch, or you just set up your Ka expression as usual. We will pick up in the next problem with some titrations. But either way, I will see you then.